Hey guys, as we wrap up this section on volume of solids of revolution, we're going to look at one more scenario here, and this is very similar to the disk method. The only difference meaning that we're going to call this the washer method. Okay, a washer, don't think of a dishwasher or a washing machine. Think of a washer that is like a tool. If you don't know what a washer is, basically a washer is it's like a little metal piece like that, and it has a hole in it, and it's used with like bolts or screws, things like that, to basically hold it through so it doesn't, go through the hole or whatever, the head of the bolt. So a washer looks like that. Okay, it's basically two circles, concentric circles, and there's a hole in the middle. So that's a hole. That is what a washer looks like. So what makes this different from the disk method? We're going to do the same exact process. We're going to basically rotate something around an axis. In this particular problem, we're rotating it around this red line, this axis here. So we rotate it around, and we get this same deal. Now the difference here, if I were to shade this in, would be when we look at this thing, it's going to have a hole that goes through the middle of it. So if I were to kind of try to draw this here, it's going to have like a little tunnel. I'm going to use just dotted lines here, simulate a hole through. If you're like an AED, you guys are probably better than I at drawing this. So it's a solid with a hole through it. So there's kind of I guess this would be solid here, but you could say that there's a hole running through the middle there. So this would actually be solid, look solid on the outside, but there's a hole going through the middle, right? So when we cut this into slices, like we've been doing, right, like this, each of these infinite number of slices, remember there's an infinite number of these, we add up the area of those infinite slices, that gives us a volume. Each of these slices would be sort of like this, and there would be a hole in the middle of it. Okay, so that would create a washer. So when we calculate the volume of this thing, or the volume of the solid overall, and we look at the area of each of these individual little slices, well, the area of this amounts to basically the area of the outer circle, area of outer, minus the area of the inner. Because if there's a hole in the middle there, we want to subtract that area out of the whole thing. Because if we were to just find the area of the outer circle, well, that would give us a solid disk. That would tell us the whole area of this. However, if we subtract out that little circle in the middle, if we subtract this out, then we're just left with the part that we want, which is all of this space around here. So we did the outer circle, subtract out the hole in the middle, then it leaves us with all the space in between. Okay, so that's the concept that we're going to apply to this scenario. So with let me go ahead and clear this. With the washer method, again, very similar to the disk method, the volume is still the area from A to B. Now, instead of just doing pi times the radius squared, we have to consider two separate circles on this one because we have sort of the outside circle and the inside circle. So it's just sort of the outer area minus the inner area in layman's terms, right? Now, when we look at this more practically, each of these circles is going to be pi r squared, right? We could kind of call the outer one, you could refer to that as big R, if you will, big R for the radius, and maybe the inner one refer to little r for the radius. Both of these are going to have a pi, so we can actually just sort of factor the pi out because they're both pi r squared, right? So I'm just going to actually write the pi on the outside this time. Pi from A to B. And then both of them are just pi r squared, so this is just going to be big R squared minus a little r squared, let's say dx. Okay, so it's just the outer radius squared minus the inner radius squared. And again, each of those have a pi. You could also just, if you want to, since we typed it in, think of it this way, pi, and then big R squared minus little r squared dx. And that's the way that I'll probably type it in. It's like that. Okay, so it's just the outer radius squared minus the inner radius squared. Before, with the disk method, again, we just had one radius because there was not that hole in the middle. This one we have to consider two radii or radiuses. Okay, so I would write that down, and let's go ahead and try it on this specific problem. All right, so we've got a function. Let's go ahead and just label on here what this stuff is. We've got a function e to the x minus 2. All right, so this is our function e to the x minus 2. All right, and then it says that we're enclosed here by x equals 0, so that's here. So we've got a boundary here, and x equals 3, so we're bound there. And we're also closed in here by the horizontal line. So this is kind of the additional thing. We're closed in by a horizontal line, -5. So that becomes our area here, right? And then we've got a little gap because we got a gap of 1 to get to our axis of revolution. Okay, that's what we're revolving it around here. This is our axis of revolution, which is the line y equals -6. So here's what we're revolving around. And you'll see again, there is a little gap from the axis of revolution to where we're starting our area, and that's what creates the hole. All right, so let's go ahead and set this up. Volume equals our integral from x values from 0 to 3 of pi. And now we have to think of what is our outer radius and our inner radius. And we've got to square each of these individually. It's not the whole thing squared, it's our outer squared minus our inner squared. So our outer radius is going to be represented by the distance from the function, so any point on this function, right, to the green axis there, right, axis of revolution, and that's -5. Now remember, when we're looking at sort of the radius, if the function's above it, it's just going to be the function value minus the axis. So generally, if this was just around the x-axis 0, it would just be the function minus 0, or just the function. But we're revolving around -5. So it's going to be e to the x minus 2 minus -6, sorry. Minus -6, okay? And that squared. If you wanted to, you could sort of put this in parentheses. So that's our function minus the axis of revolution squared. And that gives us our first radius, right? And then we have to, a lot of parentheses here. So it's this, and then minus, okay, because we want that whole thing, minus, and then our inner radius. Now our inner radius is just a line actually here, okay? That is just the line y equals -5, okay? So the distance from here to here, you could probably just use logic to figure this out, but that radius is just going to be obviously just 1, right, from -5 to -6. But how we technically write that would be -5 minus -6, because it'd be whatever that function is, in this case y equals -5, minus the axis of revolution, which is -6. And then again, that would give you 1. You can also just tell using logic that that's going to give you 1. Okay, and that would need to be squared, and then close this thing all up, and dx. Boom. All right. So like before, we're going to be doing this on our calculators. Now, I probably wouldn't type in all of this stuff. I know I said that in the last video, but some of this makes sense to simplify a little bit. So again, obviously, this is just 1. Okay, and if you wanted to combine these, you surely could. E to the x. That minus minus becomes a plus, so -2 plus 6, which would be +4. All right, so that's probably how I'll type this one in, just to make it a little simpler. So what I'm going to type into my y1 is pi, and then parenthesis, e to the x and then plus 4, close parenthesis, squared. And actually, sorry, I should do a double parenthesis. So here's what I'm typing in. Pi parenthesis e to the x plus 4 squared minus parenthesis 1 squared. And again, you know what 1 squared is, but I would probably type that one in to get used to the sort of the layout here. So it's going to be e to the x squared minus 1 squared, close parentheses at the end. Okay, so then we'll graph it. And want to then integrate this. Integral of 0 to 3, volume of this equals and I'm not actually even seeing the function. It's apparently way up there. But when you evaluate this, I got 1253 point, and we're doing the nearest thousandth again, so 177. All right, so this one has a big volume. Let's go ahead and type that in. 1253. All right. Let's go ahead and look at the next one. All right, this one's actually 2 functions, so that will be fun. All right. So it looks kind of crazy here. This one, when you revolve it around the axis, this would be a fun 3-dimensional shape to draw, especially if you're in again, AD or RAM, I suppose, too. You guys do things like this. It's going to have this sort of hole that goes through it like this. Again, I'm not an expert at this, although I did take drafting in high school. And I don't know, something like this, right? And some sort of solid. It kind of looks like a Pac-Man type deal. All right, sort of like that. And when you rotate this, it is going to have your slices that when you cut these out, will be just filled in a little bit here and here, and then again a big hole in this one. Okay, and then as you move this way, sort of the same deal, might be filled in a little bit more. And then way out here, these slices are just going to be barely filled in here and here, and a giant hole through the middle. All right, so let's go ahead and write this one out. I'm going to erase this. All right, let's figure out, first of all, which function is which, so we make sure we get the top and the bottom correct. So let's go ahead and label that. The one is a natural log, so that's got to be the curved one because the other one's just a linear function. So the top one is going to be our ln of x, and then the bottom one is our 3/4 x minus 2. All right, so we're going to do the top minus the bottom, or the outer squared minus the inner squared. So our volume, now actually for this one, it doesn't tell us anything about a limit. So we do need to find those 2 limits first of all. All right, so remember to do that. What I'm going to do is type these 2 into y1 and y2. So I'm going to type in ln of x. And into my y1. And into y2, we're going to be typing in 3/4 or 0.75 x minus 2. Graph those. And then we want to do the intersect function. Second calc intersect. And the first one I got 0.1516. I'm going to just write it all out. At least that many, it should be fine. All right. And then my second one got upper limit 4.74192. All right, that should work. And now let's think of, let's go ahead and write pi so don't forget that. And it's going to be our outer radius squared minus our inner radius squared. So visually, our radius, again, is from wherever the axis is to the outer function first. So that's always going to be the function minus the axis. In this case, it's going to be natural log of x minus, and our axis here is the line y equals -4. So minus -4, I'm just going to go ahead and put +4. Okay, squared. This is outer squared. And let me get through an extra parenthesis in there. Outer squared minus our inner function. So inner is going to be the inner function, the closer function to the axis. And that is the function 3/4 x minus 2 minus -4. So that's going to become +4. I'll go ahead and write it here. So +4, because again, it's minus -4 squared. Another set of parentheses, dx. All right, from there, again on this one, probably before I type this one in, I would just combine these to make this +2. But everything else should be good. So I'm going to type into my y1, pi, parenthesis, ln x plus 4 squared minus parenthesis 3/4 x plus 2 squared, close parenthesis. I'll pause it while I do that real quick. Okay, so then I'm going to do the integral of that, right, from those two limits we had here of this function. And let's see what we get here. 0.151635. And upper limit 4.74192. That volume should fill in that hole. On my calculator, it looks kind of like this. And it fills in this whole area up to here. If it goes like outside of that, if it starts to like filling in down here or something, that means you probably did it wrong. Or if it just like fills up part of the section, generally that's an indication that you might have done it wrong. And the answer that I get is 30.80. Nearest thousandth would be 3. 30.803. Let's go ahead and give that a shot. Let's see what we made a mistake here. Let me double check that. And looking at my calculator, it looks like I forgot to put the pi in when I typed it in my calculator. So let me add that to the end and see what that fixes here. Hopefully that was the only issue. I think I mentioned in the last video that pi is easy to forget, which I just did. So double check that. 1635. 4.74192. All right, and pretty similar result. It's just going to change our answer here, not about like multiplying it times 3. And that does give us 96.770. All right, let's try that one. Hopefully that was the only issue. 96. All right, that did it. Okay. Here's the 3D thing of it. It's kind of cool. You can see it there. I don't know, at least I'm fascinated by that. And here's the explanation, area of a washer. You can see they use the big R for outer, little r for inner. Same deal. All right. So that is the washer method. As you're doing this, if you're getting it close but missing it, let me know. If like an 8's kind of a lot of problems, I know, but if you're getting close and you got the idea and you've tried like 12 or 15 of them and you can't get it, I understand. Just send me an email or a comment and let me know. And I'm not gonna give you a 0 if you can't get more than a couple right. But let's go ahead and do the last one because this one has the axis above it, so change things just a little bit for us. So in this one, same setup. Just going to do the abbreviated version. We are going from these two places, which it does not tell us where these intersection points are. We've got two functions. So we've got an outer function from here to here and an inner function from here to here. The outer function in this case will actually be the linear equation, which is the straight line, 1/3 x minus 1. And then the inner one will be our natural log function. Okay, so this is our outer, and this is the inner. All right, and again, it doesn't tell us those intersection points, so let's go ahead and get those real quick. Type those into y1 and y2. First one I got was 0.42368, and the second one, move it over. I got 9.86784. All right, so that should be good. Now let's think about what our outer radius is. Since the axis is up here above it, we're going to do the axis minus the function. That's going to tell us the gap between them. Always just think of sort of the top function minus the bottom. In this case, it's the top function is actually the axis, right? And then the bottom function is the sort of the farthest one away. The outer radius is going to be the farthest one away. So that's going to be the function. So our inner radius, I'm going to write the pi, outer radius from the inner part there, which is 6, minus, and then the function. And make sure you use a parenthesis here, 1/3 x minus 1. Close parenthesis, squared. That's the outer radius. Outer, that whole thing. In this case, it happens to be the axis of revolution minus the function. Okay? And again, that's the furthest one away. That's the outer function. And then I'm going to throw actually one more parenthesis here. Minus, parenthesis, our inner radius. Same deal. It's going to be the axis, 6 minus, and then the inner radius is natural log of x. And then close parenthesis, squared, close parenthesis, dx. All right, so pretty much type that in like it is. Go ahead and do that real quick. All right, and what I got when I typed all that in, hopefully we did it right this time, 217.736. All right, so let's try that and make sure I put the pi in, double check. All right, I did it this time. And let's go and type it in. All right, we did it right. Okay, so again, I know these are not easy. Do the best that you can. Most important thing is that you get a firm understanding of how to do this. And if you are struggling, please feel free to reach out to me.